Alright class, here we are. We have arrived at section 5.3. We're looking at graphs of polynomial functions. So a couple of things here. So a polynomial function of degree or 2 has graphs that do not have sharp corners and no breaks. So that's kind of what we're looking at when we look at the following example. So here, which of the following graphs represents a polynomial function? So let's label this one A, B, C, and D. So of these graphs, remember, we're going to come back to this definition here. Do not have sharp corners and do not have any breaks. So for graph A, we can see here that this doesn't have any sharp corners or any breaks, so this is a polynomial graph. Right? Now when I look at B, though, we have a sharp corner, right? This is actually an absolute value function here, but this, so therefore not a polynomial. If we look at if we look at B here, notice how it curves, nice curvature, no sharp corners, so this would be a polynomial. And now when we look at D, there is a break here. So because there's a break, this is not a polynomial. So again, when we're looking at polynomial graphs, we are looking that they do not have sharp corners and have no breaks. Alright, let's continue here. Recall that if f is a polynomial function, the values of x for which f of x equals zeros are called the zeros of f. So this basically, anywhere we're intersecting the x-axis are the zeros of f. Sometimes they're also known as the roots, right? So the x-intercepts are the same as the zeros. Sometimes they're called the roots. Okay. So find the x and y intercepts. Oh, hold on. The process for finding the zeros of a function are the same for finding the x-intercepts of the function. So we want to find the x and y intercepts of this function here. Alright, so f of x equals x cubed minus 5x squared minus x plus 5. So in order for us to find the y-intercept, right, it's always the easiest one to find. All we want to do is we want to let x equal 0. So if we plug that in, we're going to swap the f of x for the y, and then we're going to plug in 0, so we'd have 0 minus 5 times 0 squared cubed minus 0 plus 5. So we can see that the y-intercept is 5. But we'd write this as a coordinate as 0, 5. Alright, so now let's look at the x-intercept. So the x-intercepts, we set y equal to 0. So here we'd have 0 equals x cubed minus 5x squared minus x plus 5. Alright, so in order for us to solve this, we're going to go ahead and do factor by grouping. So let's group these two together and these two together. Let's change colors here. And so x cubed and negative 5x squared have an x squared in common. So we'll have x minus 5. And then here we're just going to pull out a negative, so negative 1, and then I'll have x minus 5. Now I have an x minus 5 and an x minus 5 in common. So we're going to pull that out, x minus 5, and I'm left with x squared minus 1. Now x squared minus 1 here, this is a special factorization. This is called the difference of squares. Okay, and the difference of squares tells me that if I have a squared minus b squared, that this is equal to a minus b times a plus b. So that's what's happening here. So this is going to be x minus 5, x minus 1, x plus 1. Okay, so now I've factored this out as much as I could. These are all prime now, and so let's go ahead and set these equal to 0. So I have x minus 5 is equal to 0, x minus 1 is equal to 0, and x plus 1 is equal to 0. So therefore x must equal 5, x will equal 1, and x will equal negative 1. And so our x-intercepts, or our zeros here, as coordinate points would be 5, 0, 1, 0, and negative 1, 0. And there are our zeros. All right, let's look at finding the x-intercepts of this function using a graph. Alright, so we're going to go ahead and use the Desmos graphing calculator. So I'm over here. I already plugged in our equation, x cubed plus 4x squared plus x minus 6. And so we have this graph here. Now, if we take a look, we're going to be looking at the zeros. Again, those are our x-intercepts. So we have negative 3, 0, we have negative 2, 0, and then we have 1, 0 for our x-intercepts, and our y-intercept is down here at 0, negative 6. So those are our important points there. So let's go ahead and write this down. So it only told us to find the x-intercepts actually. So our zeros, or x-intercepts, are going to be negative 3, 0, negative 2, 0, and 1, 0. And that's it. Alright, so graphical behavior of a polynomial, of polynomials of x-intercepts. So if a polynomial contains a factor of the form x minus h to the p, the behavior near that x-intercept h is determined by the power p. So we say that x is equal to h is a zero of multiplicity p. The graph of a polynomial function will touch the x-axis at zeros with even multiplicities. The graph will cross the x-axis at zeros with odd multiplicities. The sum of the multiplicities is the degree of the polynomial function. Okay, so this is all about multiplicities. Okay, so let's take a look through an example. Right, so let's take, for instance, this graph here. So when we're looking at this graph, we have f of x equals x plus 3, x minus 2, and x plus 1. So x plus 3 has multiplicity 1. So this is telling us that we have an x-intercept at x equals negative 3. So at negative 3, here's our dot. Because it is an odd multiplicity, right, then if we're looking back up here, the graph will cross, let's highlight this, the graph will cross, there it goes, the x-axis at a 0 with odd multiplicity. So here we have a 0 with odd multiplicity. So notice how it is crossing that graph going downwards here. Now the next one, x minus 2, has an even multiplicity. And so since it's an even multiplicity at x minus 2, that's over here at 2. And notice how the graph kind of comes down and it comes back up. So it's bouncing, it's touching at 2 because of that even multiplicity. Now our last one here is we have x plus 1, which is an odd multiplicity of 3, and that's our 0 here. And so again, notice how our function kind of goes through, okay, and that's again because it's going to cross the x-axis with an odd multiplicity. But with that even multiplicity, it will touch the x-axis, right? And so that's what's happening here. So, oops. So notice, so we're crossing, it crosses with those odd multiplicities, but it bounces with that even multiplicity. The closer the graph looks to be linear, the more likely it has multiplicity of 1. So notice how this one looked like a linear function, but this one did not. Neither did this one, right? So that meant that this one was closer to being a multiplicity of 1, and we saw that it was. Oops, there we go. All right. The zoom is like... Alright, here we go. Use the graph of the function of degree 6, excuse me, degree 6 to identify the zeros of the function and their possibility of multiplicities. So let's take a look at these. So first we want to identify the zeros that we have. Okay, so let's list the zeros. So we have one here at -3. We have one here at -1. And then we have one here at +4. Okay. Now let's ask ourselves, are we crossing or are we bouncing? And so at -3, we bounced. At -1, we crossed. And then at 4, we also crossed. Okay, so because we did that, that means that we were really looking at, when we look at even and odd, right, which one are the possibilities here? So because we bounced, that's going to be even. So what are our possibilities for even? Keeping in mind that we have a degree 6 polynomial. So keeping that in mind, we know that our possibilities here, we could have 2, 4, 6, right? Those being the highest. Okay. We know that this is an odd, so the possibilities are 1, 3, 5. We know this one is an odd, and the possibilities are 1, 3, 5. So let's take a closer look at these possibilities. Because we have 3 zeros and the other 2 are odd, 6 doesn't make sense. Because we have 5, that means that this one, if this was a multiplicity of 5, then that means that this one could not be a multiplicity of 2. Right? Because there's my degrees. So 5s doesn't make sense either. So really this is what we're left with. So there's some type of combination here. So for number 1, our possibilities are going to be our x plus 3, and it's either going to be to the 2nd power, or x plus 3 is going to be to the 4th power. Okay. Now we can also have x plus 1 is going to be either to the 1st power or it's going to be to the 3rd power. And then we can have x plus 4, again, is going to be to the 1st power, or it's going to be to the 3rd power. Okay, so these are the possibilities we have. Let's take a look at turning points. So interpreting turning points here. A turning point is a point on the graph where the graph changes from increasing to decreasing, or decreasing to increasing. A polynomial of degree n will have n minus 1 turning points. So let's take a look at a couple of examples here. Find the maximum number of turning points for each polynomial function. So here notice that we want to take a look at the highest degree. So what is going to be our n? And normally we write our polynomial in ascending order or descending order, but in this particular case, notice that this one is hidden right there. So that is going to be 5th degree. And so since n is 5, then n minus 1 would be 5 minus 1, which gives us 4. So it's going to be 4 turning points. So it's going to have a maximum of 4 turning points. So now on this one, it's not as easy to see because it's in factored form. So notice we have a 2 here, and we have a 2 here. So if we were to take a look at this, right, so this would mean we would have x to the first times an x to the first, and then we'd end up multiplying that by a 2x squared once you factored all of this out. And so because of that, we'd actually really end up with an x to the 4th, 2x to the 4th when you multiply all those values out. So that means that we are looking at a degree of 4. So our maximum number of turning points here is going to be 4 minus 1, which is 3. So we have 3 turning points there. All right, let's take a look at the next example here. We want to sketch the graph and f of x equals -2 times x plus 3 squared times x minus 5. Then we want to use a calculator to verify the results. So let's take a look at here. So what zeros do we have? So we have, notice because we are going to set this equal to 0, we're going to get a 0 at x equals -3. Here we're going to set this equal to 0, and we're going to get a 0 at x equals 5. So we have 2 zeros, one at -3 and one at 5. What's happening at these zeros? So because this has an even multiplicity, right, we know that there's going to be some type of bounce. Okay, since this one is odd, we're going to go through, so we're going to cross the x-axis. So this is good for us to know. And this is based off of the power here, so notice that we have an even here, and there's nothing here, which means that that's a 1. So let's come over here and go ahead and plot these points. So we're going to have one at +5, so here's 1, 2, 3, 4, 5. Here's our 0, and then we have one at -3, so 1, 2, 3. So at -3 we are going to be bouncing. The other thing to notice, right, is we do have a -2 up here. Okay, and so what does that look like for our graph? So let's take a look at some of the other functions. So we have our a is negative. So if we think about our end behavior, our a is negative, but our degree is 3, which is odd. So that means that based off of because our a is negative, we're going to have something that looks like this. Okay. And this is back, from, I think, section 5.1. So what does this mean? This means that on this side of my 3, we're going to look at something like this. It's going to be coming up. But on this side of my 5, I'm going to be coming downward. Okay. I know that there is a bounce on 3. So it's going to kind of, maybe it'll go like this. Right? So because it's going to kind of hit and bounce back up. Maybe that's a better description there. So it's going to hit and kind of bounce back up. So this is kind of what the graph should look like based off of the different facets here of the polynomial equation. Let's take a look at Desmos and go ahead and check out the graph. Alright, so here's the graph. We can see if we can fix this window a little bit. Let's see here. Alright, here we can see the graph now. So notice how we're coming all the way down. We bounce on -3, we come right back up. We do hit the y-intercept at 0, 90. So it is pretty high in terms of the scaling of the graph, or high numbers, right? We reach a maximum here at about 2.3, the x value, and come back down and go through the graph at 5. So notice that we did a lot of this graphing, and even though it doesn't, we would be really looking here at pretending that this is 90 here, but we can see that we kind of graph that based off of the end behavior and what's going on with the zeros. Alright, so now we have arrived to the intermediate value theorem. This is one of the most important theorems we're going to see in this particular course, and you will need to kind of remember this for calculus because you'll be seeing it a lot in calculus as well. So the intermediate value theorem tells us that if we let f be a polynomial function, the intermediate value theorem states that if f of a and f of b have opposite signs, then there exists at least one value c between a and b for which f of c equals 0. So basically what we are saying here is that if we have a point, this one, where f of a is negative, and then we have a point here where, let's call this point right here, where f of b is positive, there is a point in between where there exists some letter c such that the function is going to equal 0. So that is what the intermediate value theorem is telling us, is that if we have two values in an interval, a to b, there's a value c somewhere between that interval that must be 0 if f of b and f of a have different opposing signs. And so we can see here through this visual that, well, of course, right? I hope it feels kind of obvious that this has to exist, because the only way we can get that change of sign is if at one point we cross the x-axis. I do want to say one thing before I move on, that the intermediate value theorem, sometimes we will see it as the IVT, and so it just gets shorthanded that way. But yeah, so that is one of the big theorems that we're going to be seeing here. So let's take a look at an example here. So given the following table of values of the polynomial f of x, what is the minimum number of zeros of f of x that guarantee to exist by the intermediate value theorem? So let's take a look at this. So here are x values, here are y values. So look at from here to here, there is one change, right? Because I'm going from, in an interval from 1 to 2, I'm going from a negative to a positive. Then I'm going from a positive to a negative. That's another time. Here I go from a negative to a negative, so that's okay. But then over here, I'm going from a negative to a positive again, and so that's another one. Okay? So in total, that's telling me that that's 1, 2, 3. So the intermediate value theorem is telling me that there is guaranteed a minimum to have 3 zeros. Okay? So let's write that down. So by the IVT, we are guaranteed 3 zeros. So again, every time we're looking at the intermediate value theorem, we're basically looking how many sign switches. Okay, and that's what we were looking at there. Alright, show that the function f of x 7x minus 9x to the 4th minus x squared has at least one real zero between 1 and x equals 1 and x equals 2. Alright, so here we're looking basically to apply the intermediate value theorem, but first we need to figure out what is happening with f of 1 and f of 2, so we need to identify that first. So we figure out, okay, well, what is f of 1? So let's plug that in. So we get 7 to the 1st power raised to the 5th minus 9 times 1 to the 4th power minus 1 squared. Okay, so when we plug that into our calculator, right, we do get a negative 3. And then we go f of 2, let's plug in 2, so 7 2 to the 5th power minus 9 2 to the 4th power minus 2 to the 2nd power. Alright, and so then we get 76. But this is a positive 76. So now notice that we got a sign switch. So we got that sign switch there. That tells us that by the intermediate value theorem, we can say that there exists at least one zero in the interval 1, 2. Or you could say between x equals 1 and x equals 2, but that's saying the same thing as this interval. Okay. All right. Let's look at the next example here. Given the polynomial f of x equals 3x cubed minus 4x squared minus 3x minus 1, what is the smallest possible integer a such that the intermediate value theorem guarantees a 0 that exists between 0 and a? All right, so let's take a look at this. So let's go ahead and, because we're starting with 0, so let's first find out, well, what is 5 of 0? What's f of 0? So f of 0 is going to give us 0 cubed minus so this is going to give us a negative 1. So we're really looking for, okay, well, when are we going to be able to get that positive value, right? Because that's when that sign is going to switch. So if I plug in f of 1, right, we're going to get 3 to the 1st minus 1. So we plug that in, we're going to get negative 5. Okay, well, that's not. Let's try 2. So we get 3 times 2 cubed minus 4, 2 to the cubed, whoops, square. So when we plug this in, we actually get 1. And so here we finally got that positive value, that positive sign there. So from here, there is no sign change, but I do get a sign change here. And so therefore we can see that our smallest value is going to be a is equal to 2. Okay. All right. Factored form of polynomials. So if a polynomial of the lowest degree, p, has a horizontal, let's take a look at this, has horizontal intercepts x, then the polynomial can be written in factored form such as this, where the power pi on each factor can be determined by the behavior of the graph in corresponding intercepts. And the stretch factor a can be determined given a value of the function other than the x-intercept. Alright, so let's figure out how to do this. So first we're going to identify the x-intercepts of the graph and find the factors of the polynomial. We're going to examine the behavior of the graph at the x-intercepts and determine the multiplicity of each factor. Find the polynomial of least degree containing all the factors found in the previous step. And use any points of the graph, the y-intercept may be easiest, to determine the stretch factor. Alright, so we are going to be working this backwards from a graph to finding the equation. So here we're going to write a formula for the polynomial function shown below. Alright, so let's start off by identifying our zeros. So we have a 0 here, here, here. So our zeros are going to be -3, and then we have 2, and then we have 5. Okay, and so are they even, odd? What's happening here, right? So because at -3 we are crossing, this is going to tell me that we have an odd degree. At 2 we are bouncing. This tells me we have an even degree. And at 5 we are crossing, so we have an odd degree. So what are the possibilities here? Well, I know that the overall is going to be an even degree, so the polynomial is going to be even degree. And I can tell that because we have something like this. Okay. All right, what else do we know? We know that how many turning points do we have? Well, here's one turning point. Here's another turning point. And here's another turning point. So we have 3 turning points. Okay. So remember, turning points are n minus 1 equals 3, so therefore n is 4. So we are looking at 4 degrees. So what are the possibilities for odd functions, right? So for odd, we could be looking at 1 or 3. We could be looking at, for even, we could be looking at 2 or 4. And again, for the odd, we could be looking at 1 or 3. Right, in terms of the multiplicity or the power. But because we know that, sorry about that, class. Still not feeling 100%, but because we know that we have a degree of 4 here, right? So which one of these multiplicities are going to make sense? So 3 would be too high. It wouldn't be 4. 3 can be too high. So we're really looking at something like this in order for it to add to 4. So our polynomial is going to be f of x. We are going to take the factored form. So we're going to have an a times our x. Now let's write this as a term. So it's going to be x plus 3, first degree. And then we're going to have x minus 2 to the second degree, and x minus 5 to the first degree. Okay, and I know this because this one has to be an even multiplicity, which is 2, and since we know it's a degree 4, then the other 2 must be 1, so then I get 1, 2, 3, 4 degrees. Okay, so let's go ahead. So now that we're here, we need to figure out, okay, well, how do we calculate our a? So the way that we're going to calculate our a is we're going to find the y-intercept here. So here we have our y-intercept, which is given to us at 0, -2, and this is what we're going to plug in. So we're going to have -2, a, and the nice thing about this is that, you know, we're really plugging in 0 for x's. And so here we end up with a times 3 times -2 squared times -5 to the first power. Here's our -2. So we're going to go ahead and multiply this out. So 3 times -2 squared times -5, that gives us a -60. 60a, and this is a -2. We're going to divide both sides by -60. And so we get that a is equal to 1 over 30. So this is our a. So this means that our polynomial function is going to be f of x is equal to 1 over 30 x plus 3, x minus 2, and x minus 5. And that's it. Okay. That's it for that one. Alright, next, use the given information about the polynomial graph to write the polynomial in factored form. So here we're getting information, so we don't have the graph, but we're getting information, turning it into a polynomial. Alright, so we know we have a degree 5, so our n is 5, our leading coefficient a is 1, and we have these following zeros. So we have, I'm just going to write these as factored form. So this would be x minus 1, and then I have x plus 9, x plus 2, and x minus 2. And we have a y-intercept of negative 0 and negative 180. Okay, alright, so we know what a is, but we are missing, we only have 4 x values. So we're missing one value. So we're missing an x. Let's go ahead and call it an unknown 0. Call it x minus z. So let's go ahead and write out our formula. So here's our polynomial, our f of x. We have a. And we're going to have all of these values here. X plus 2, x minus 2, and x minus z, which is our 0 that's missing, our unknown fifth 0. We have our y-intercept is 0 is negative 180, so let's plug that in. So we're going to get negative 180. Our a we already know is 1. Okay, so then when we plug this in, we're going to get 0 minus 1, 0 plus 9, 0 plus 2, 0 minus 2, and 0 minus z. So what do we get here? This gives us negative 1 times 9 times 2 times negative 2 times negative z. This equals negative 180. So here this gives us a negative 9. This gives us a negative 4. Negative 9 times 4 gives us a negative positive 36, but we get a negative there, so this is a negative 36z equals negative 180. So let's go ahead and divide both sides by negative 36. Okay, so then we end up with z equals 5. Okay. So what's our polynomial function then? So our function would be f of x equals 1 because of our a. Then we have x plus, x minus 1, x plus 9, x minus 2, x plus 2, and then lastly x minus 5. This is our polynomial function based off of the conditions that were given to us. Okay? And I think that's it. We're all done.